In this video, we will explore the effects of special relativity on the momentum. In previous videos, we have seen that special relativity is based on two fundamental postulates. 1. The laws of physics are the same in all inertial frames of reference. 2. Light travels in a vacuum with the same speed c in any direction in all inertial frames. For the discussion on this video, we will focus on the first postulate. As we know, in order to have a good theory, it has to reproduce the results of classical physics. In this sense, we need to answer the following question. Is the momentum conserved under Lorentz transformations? To answer this question, let's think of the following case. Suppose you have two reference systems, S and S'. Also, there is a particle moving with respect to S', with mass m, and speed u. We have to remember what the Lorentz transformations are for the speeds. When one-dimensional motion is considered, Lorentz transformations are the following. Unfortunately, momentum is not conserved under the Lorentz transformations when we observe an interaction in the reference frame S or S'. Fortunately, if we consider the rest reference system of the particle, we can see that the classical definition of the momentum will satisfy the Lorentz transformations only when the relativistic factor is included in the expression. Note how the relativistic factor is defined in terms of the speed of the body, and not the speed of the reference frame S'. This step is natural if you think of the proper time of the particle, and applying the time dilation equation in the differential form, as follows. Then, we see that the derivative of t with respect to tau is the following. On the other hand, if we apply the chain rule to the classical definition of the momentum, we get. If we insert the previous step into the classical definition of the momentum, we finally get the relativistic form of the momentum, as mentioned above, to satisfy the Lorentz transformations. As stated before, we have to remember that the relativistic factor is defined in terms of the speed of the particle, meaning the following. Note how we have used the subscript u to avoid confusions when using the relativistic factor. Now let's take a moment to analyze the relativistic momentum equation. As in the case of time dilation and length contraction, we can see that the relativistic factor will approach to 1 when the speed of the particle is much smaller than the speed of light. This means that we will return to the classical definition of momentum. This is an expected result, as special relativity is a complete theory. Another interesting case is when the speed of the particle approaches the speed of light. In such a case, the denominator of the relativistic factor will approach to 0. In other words, the relativistic momentum will become infinity. But this is not a correct result from the physics point of view. Then, we can say that an object with mass cannot reach the speed of light. Actually, this confirms what we have said before. The speed of light is a limit for objects and interactions to propagate. Additionally, we can see that the mass of the particle is m when measured in the resting reference frame of such a particle. This is commonly called the rest mass. Also, in some textbooks, it is usual to find the term relativistic mass defined as the product of the mass times the relativistic factor. Let's solve an example to see how the relativistic momentum works. Example 6. The mean lifetime of muons at rest is 2.2 microseconds. The observed mean lifetime of muons as measured in the laboratory is 6.6 microseconds. Find the relativistic mass of a muon at this speed when its rest mass is 207 times the electron mass. Could you solve it? Answer. As we can see, the solution has two parts. First, we need to calculate the relativistic factor using the length contraction equation. Inserting the values of delta t and delta tau, we find that the relativistic factor is the following. In the second part, we use the relativistic factor multiplied by the rest mass to get the relativistic mass. Inserting the value of the relativistic factor and the rest mass into the previous equation, we get. Finally, for simplicity, we express the relativistic mass in terms of the electron mass. Note how the relativistic mass is bigger than the rest mass. This is an interesting result as it says that the inertia of the particle increases when moving at high speed. In the next video, we will see what is the expression for the energy under special relativity. Stay tuned.